Okay, so welcome back. And so before we actually start Chapter 9, or we're going to start Chapter 9 on hypothesis testing, I wanted to discuss the idea, the big idea behind a hypothesis testing, because in Chapter 8 we discussed how we could use confidence intervals to estimate a population parameter. And so we could use confidence intervals to say that, hey, I know with a certain level of confidence that the true population parameter, whether it's the population mean or population proportion, is going to be inside this range of values that I created, that I constructed around the sample statistic, okay, using the distribution of my sample statistic, my sampling distribution, okay. And so we saw how that worked in estimating a particular value of a parameter. So now, what if we used a confidence interval to test something, okay? So when we did that before, we took an example of the doe population, right, the female deer population one, and we said, hey, let's assume, for the moment, let's assume that the deer population is healthy. So let's start with that assumption. We're going to operate under the assumption that the deer population is healthy. And then what did we do? We have this idea, we have this rule, right? The rule is, for this particular problem, the rule was that if we collect a sample of 50 deer, a random sample of 50 deer, doe, female deer, and we weighed each of the deer. So it was a capture, weigh, and release, right? So we randomly capture 50 deer, we weigh them, or we release them, and now we've got our 50 weights. And we calculate the average of those 50 does. So here's the rule, if the average weight of the 50 deer, or the 50 doe, is less than 60 kilograms, that's what it was. Was it 60 kilograms? I believe it was, was it 60 kilograms? Yeah, yes, that's what it was. It was less than 50 kilograms. So if the average weight of the 50 deer was less than 60 kilograms, then the rangers would deduce that the population was unhealthy, that the deer population was unhealthy. That was the rule, right? And so what we did was we calculated the probability of actually getting that sample. And we found that the probability of getting that sample was very small. I think it was 0.0014. Okay? And so the idea here is that we used a confidence interval to say, we found that the probability, this is Chapter 7, I'm sorry. So in Chapter 7, we saw that the probability, right, so we took a random sample of 50 deer, right, and we found the sample X bar, right, and we said if, so here's the rule, if X bar is less than 60 kilograms, then our conclusion is that the deer population is unhealthy. And so that was the rule, right? So now what we said was, okay, well, what is the probability of getting such a sample? Okay? So what is the probability of getting a sample that has an average weight of less than or equal to 60 kilograms? Okay? Okay. And so this is where the distribution, right? Remember Chapter 7. So this was Chapter 7 that we're talking about. So in Chapter 7, well, in order to calculate this probability, we had to know the distribution, right? And so we knew that the distribution of X bar in this case is normally distributed with a mean of what? A mean of 60 kilogram, or what was it? It was a mean of 63, was it 63 kilograms? Yeah, I believe it was a mean of 63 kilograms and a standard deviation of, well, for X bar, what was it? It was the standard deviation was, I forget the number, but it was some number and we had to divide by 50, right? And so what we did was we found that the probability of this sample, of getting this sample, was really small. Okay, I think that was the number, but anyway, the point is it was really small, right? But we started with an assumption, and we said, okay, now, what if we did get that sample? Okay, what if we start with the assumption that the deer population is healthy? Right? And what if we collect data, right? We randomly select 50 deer, so we collect a random sample of 50 deer and we weigh them, and we find that the sample mean for the 50 deer turns out to be, let's say, 58 kilograms, right? Well, what we would say is, what is the probability of getting a sample statistic that is equal to that or more extreme than that? Which means, since our rule is less than or equal to or less than 60 kilograms, what if we find the probability of getting a sample statistic equal to 58 or less than 58? And so what we can do is we can find the probability that X bar is less than or equal to 58, okay? Or if we want to use the rule 660, okay? And based on the distribution of X bar being normal, okay? And of course, the central limit theorem gives us that in this case, so we know that X bar is going to be normal, right? With a particular mean and standard deviation, okay? And what we're going to do is we're going to find the probability of getting a sample, getting that sample, right? So we got that sample, right? So what's the probability of getting this sample statistic or something that's even more extreme? Well, that's this. And so if we find this probability, right, what if that probability is really, really small? Okay? For example, remember in previous discussions, in the previous videos, we said if the probability of such an event is less than, what, 0.05, that's considered an unusual event, right? And if we, remember, if we go out to 2 standard deviations, and for a normal distribution, the probability of being less than, if we go out to 2 standard deviations, we can find, or 3 standard deviations, right? If we go out to 3 standard deviations, we're talking about a very small probability of being less than or equal to this value, right? So if our probability of getting that sample is significantly small, then we only have 2 options, right? Either we can conclude that we're really lucky, and this is just coincidence. We got a really rare event, right? We're just lucky. It's just coincidence. You know, we should probably play the lottery or something, right? Or we're not lucky, and our assumption's wrong, because if we calculate this probability based on an assumption, and we find that, wow, based on this assumption, getting a sample like this is extremely rare. Well, either we're really lucky and this is just coincidence and it's a fluke and we just happen to get it by random chance, or our assumption is wrong. Now in statistics, we're going to say, hey, we're not that lucky. We're going to say that our original assumption is incorrect, and so the sample is giving us evidence against the assumption. Does that make sense? I hope that makes sense. So in other words, we're going to use sample data and we're going to find the probability in one of the methods that we're going to use and find out if that probability is significantly small, and we're going to define what significantly small means later on. But we're going to say if that probability of getting that sample that we just got is significantly small, then that's going to be evidence against the assumption that we're making. Okay? And we're going to talk about what that assumption is. Okay? And that is the crux of a hypothesis test. We're going to start with an assumption, we're going to collect data, and we're going to find, based on the sample statistic, we're going to see if the sample statistic and the data is evidence against the assumption or not. Okay? And that's the big idea behind a hypothesis test. Okay, we make a claim, and then we make an assumption, and then we collect data, and based on the data, we either see if there's evidence against the assumption or not enough evidence against the assumption, and then that's going to tell us what to say about the claim. Okay, and that's the big idea behind a hypothesis test. So let me use this example here, and this will be the end of the video. And this is, again, just the big idea. The next video will start to piece it all together as far as the steps of a hypothesis test, and we'll get into the analytical part. But right now, this is just to give you an idea of how a hypothesis works. Okay? So let's say that we have Nissan. Nissan dealers have a certain car, right, and a braking system. And they've always assumed that the average braking distance for all of their cars, for these types of cars, okay, is 175 feet. So up until recently, we've assumed that the average braking distance for all of these cars, based on this braking system, is 175 feet. Okay? Now, the engineers come up with a new braking system that they believe is better than the old braking system. Okay? Well, what does better mean? Well, in this scenario, in this context, better means that it would have a shorter braking distance, right? If it's a better braking system, you would expect the car would stop in a shorter distance, right? So they're claiming that this new, so now we have a new braking system, okay? And they're claiming that it's better. So they're going to claim that for the new braking system, the braking distance for these cars operating under the new braking system is actually going to be less. So they're going to claim that mu for the new braking system is less than 175 feet, right? That's their claim, okay? So, here's the idea. Let's do it two ways. Let's construct a confidence interval. Since we just finished confidence interval, let's construct a confidence interval and see what we can conclude using the confidence interval. Okay. So now what we're going to do is we're going to collect data, and we're going to construct a 95% confidence interval for the average, the true average braking distance of all cars like these with the new braking system. Get it? Okay. So what we're going to do is we're going to construct a 95% confidence interval for mu. Okay. Now, so let's say we collect data and we collect 36 cars. We collect data on 36 cars. So we randomly select 36 cars, and we take them, we have them go 60 miles per hour, and then we slam on the brakes, and we measure the skid marks for all 36 cars with the new braking system. And so we find that the average braking distance for all 36 cars is 160 feet. Okay, now, what do we need? We need to know the standard deviation. Let's assume the standard deviation for the population is, well, let me think. Let's assume we know sigma. Let's assume we know sigma for the time being. Let's say that sigma is equal to 30 feet. Okay? And so now with this information, let's construct our confidence interval. So again, since n is bigger than or equal to 30, right? That means n, or excuse me, x bar is going to be normally distributed, right? And it's going to have a mean. Well, what's the mean? We're assuming that the mean is, or excuse me, the mean we don't know, right? Because we're doing a confidence interval. We don't know what the mean is. So, but we do know sigma. Sigma is 30, and so this is going to be sigma divided by the square root of n. Okay? So now, our confidence interval is going to be x bar plus or minus z alpha divided by 2. Why? Because we know it's normal, right? X bar is normal. And the standard deviation is sigma divided by the square root of n. Okay? And so now, what do we get? Well, it's going to be, our x bar is 160, right? 160 plus or minus, our z alpha over 2 for a 95% confidence interval is 1.96. And our standard deviation is going to be 30 divided by the square root of 36. And this whole thing becomes 5. And so what do we end up with? Well, we end up with, well, let's see, we end up, oops, 36. So we end up with 5 times 1.96, which is going to be, let's see, 19. That's going to be, so this is going to end up being, $9.8. So what do we end up with? So our margin of error becomes 9.8. Yeah, that's right. So 9.8. And so our confidence interval becomes what? We're going to subtract this. So it's going to be 150.2 and 169.8. And I believe that's right. Double check that, but I believe that's right. So now our confidence interval is this. So what does this mean? Well, this is the 95% confidence interval for the true average braking distance for all cars like these based on the new braking system. Now, what number do you see, or that is conspicuously not in this interval? The 175. That's not in the confidence interval. So, in fact, the confidence interval, the 175, actually falls above the confidence interval. So, looking at the confidence interval, we would conclude that, yes, based on the sample data, 175 is not even a contendant for being a candidate, right? It's not even a candidate for the true mean. for the population mean, for breaking distance. So this is evidence that tells us that indeed the braking system is better because the average braking distance is smaller with the new braking system than with the old braking system. Because with the old braking system, we know the average is 175. That's using a confidence interval. Make sense? So now, let's do it a little bit differently. So here's where confidence intervals come in. Or not confidence interval, but the hypothesis testing. So let's start with an assumption. So now here's the claim, right? So the claim is this, right? Now, let's assume, for a moment, let's assume that there is no difference. That with the new braking system, the average braking distance doesn't change, okay? So let's assume that mu stays the same, okay? So we're going to assume, oops. So this is the claim, but we're going to assume that mu didn't change. That mu is actually just 175 feet. Okay. So now under that assumption, so this is our data, this is our sample data, right? Now under that assumption, what we're going to do is we're going to calculate the probability of getting the sample that we got or a more extreme sample. Okay? How extreme? Well, what's more extreme than this? Well, anything that would be less, right? Remember, more extreme, we're already claiming that it's less. Well, if this is what we got, well, then more extreme would be even less than that. Okay, so it's in the direction of whatever this arrow is for this time being. So we're going to calculate, okay, based on this data here, we're going to calculate what's the probability of getting the sample statistic that we got, or one that's even more extreme. So x bar is less than or equal to what? 160 feet. Now, this is where chapter 7 comes back, because we need to know the distribution of x bar, right? So again, x bar is normally distributed, right? Because of n being greater than or equal to 30, right? So this tells us that by the central limit theorem, that x bar is going to be normally distributed with a mean of, now, here's where the assumption comes in. We're going to assume that the population mean has not changed. So we're going to assume that mu is equal to 175 here. And then we're also going to use the standard deviation of x bar, which is going to be sigma divided by the square root of n, which we found out is going to be 5, right? So we're going to use this data, right? We're going to use this information, these parameters, for the normal distribution for x bar, okay? So now we're going to use this to calculate the probability. Now, we're going to use normal CDF, okay? And the lower bound here is what? The lower bound is going to be 0, right? Braking distance can't be negative, so we could use 0 here. The upper bound is going to be 160. The next thing is the mean. The mean we're going to use is the mean that we're assuming. We're assuming the mean is 175. So we're going to put that in there. And then the standard deviation in this case is 5, right? Square root of 36 is 6. 30 divided by 6 is 5. So we can just put 5 here. Okay? So now, what do we get for that probability? We get a really small probability. I don't see, in fact, let me see if I can pull it up. I don't have my calculator handy. Let me see if I can pull it up here. And okay, so we're going to, let's see here. Okay, let me quickly do this. So I'm going to do Okay, so we have a mean of 175, standard deviation of 5. X bar is 160. So I put it, okay, so I'm putting the mean, the mu, so the mean is 175, so 5, so upper bound is 0, 1 to 60, and let's see what we get. And we get 0013. So the cumulative distribution function gives us 0.0013. So now, here's the probability of getting the sample that we got, or a sample that's even more extreme. The probability of that happening is 0.0013. Really small probability. So again, the question is are we just lucky? Or is our assumption wrong? Because that's what our probability is based on. The probability was calculated based on the assumption. But the probability of getting that sample is so small that either we're lucky and it was just a fluke, or our assumption is wrong about the parameter. So in this case, we would say, hey, this is evidence against the assumption. And so if there's evidence against this, then maybe there's evidence to support this. Maybe that means that, hey, the new braking system does in fact work, is in fact better. That's the big idea behind the confidence, or the hypothesis testing. Now, the idea of, okay, well, how small is this? Well, we're going to figure that one out later, but if this is too small, then that would be evidence against our assumption. Well, how small is too small, or what is significantly small? That's going to come up next time. Okay? Okay. I hope that was helpful. Let me know if you have any questions. And other than that, have a good night. Thank you, and I'll see you next time.